Okay. Perfect. Okay, we are continuing with the chapter 13. And we stopped here at the like splitting pattern, and some patterns that can relate to specific groups. Like if you have isopropyl group or like a T-butyl group. Let's say if you have an isopropyl group, your isopropyl group is a CH3, CH, CH3. So if you do have isopropyl group in the NMR spectrum, is going to show as, regardless of what you have on the other side. So let's say you have isopropyl group that is attached to a major carbon chain. So you have hydrogen A and you have hydrogen B. This is going to be hydrogen B. How many of hydrogen A you have is just one, and you have 6 of hydrogen B. Hydrogen A is going to be splitted by hydrogens B. And the rule which we talked about last class, it was an N plus 1. So for hydrogen A, value for N. Can someone, just as a reminder, can you tell me what is the value for N for hydrogen A based on what you see in the red diagram that I have here? It's just a partial structure. What's the value for N for hydrogen A? N is the number of hydrogen on adjacent carbons. So if you have this carbon, you have 2 adjacent CH3, you add them together, that gives you 6. 6 plus 1 is going to be 7, and is going to be septet. So it's 1, 2, 3, 4, 5, 6, and 7. So when you have these, a peak like this, and also in the neighboring or in the neighborhood of less than 2, you have peak for hydrogen B. What would be the splitting pattern for hydrogen B? Splitting pattern, that means the value for N plus 1. The value for N for hydrogen B is just 1, right? Just 1, because these two hydrogens are the same type of hydrogen, and they don't split each other, but they are going to be splitted by hydrogen A. And since you have only one hydrogen A, the value for N is 1. 1 plus 1 is going to be 2. So for this B type, we will get a doublet. And if it's a doublet, it's going to be like same height. What else we can add here? What other type of information? What other type of information we can get from here? That is that the height ratio for the A-type hydrogen to B-type hydrogen, it corresponds or correlates with the number ratio. So we have B-type hydrogen, 6 hydrogens, and then A-type is 1. So it's a 6-to-1 height. So if you have the vertical line here, is going to be 6 times as the vertical line for B-type hydrogen. So if you have these two together, that means you have a isopropyl group. So if you do have an isopropyl group here, these two groups, these two peaks kind of are responsible for the isopropyl, or these two hydrogens are coming from the isopropyl hydrogens. So it's going to be like a doublet. You do have like in this green partial structure again, you do have a for this side, for this green one, you have a CH2 also, because you have a basically this is coming from like a CH3 and a CH3 here. So you have the A and a B is coming from the A and B, And now this C is going to be doublet also. This is going to be doublet because it's neighboring to this hydrogen of A. So is the N plus 1 here is going to be 1 plus 1, or N plus 1 is a 1 plus 1, which is 2 for this C-type hydrogen. And that shows up between 3 and 4. Why is showing up between 3 and 4? We did talk about this last class because it's attached to electron withdrawing group of oxygen. So it's going to, these hydrogens of CH2 is going to be de-shielded. And if it is de-shielded, it's going to move between 3 and 4. Normally, CH2 would show, if it's an alkane, there is no electron withdrawing group attached to it. It will show at 1.2 to 1.4, like 1.2, 1.3. But if it is attached to electron withdrawing group, is going to be de-shielded and is going to move to higher number. Specifically for oxygen, if it's attached to oxygen, is going to move between 3 and 4. And that gives the location. So we have the location, we have the height ratio. The height ratio corresponds to the number of hydrogens that we have, which we need the integration line. And then we also have the splitting pattern. So the splitting pattern, because it's a doublet, it shows that it's adjacent to a carbon with 1 hydrogen, which is this hydrogen A here. That's why it's doublet. It's between 3 and 4 because it's attached to oxygen. The carbon that carries the CH2, the 2 hydrogen is attached to electron withdrawing group of oxygen. Now, what about the OH group? The OH group, or the hydrogen from the OH, this group, this hydrogen, there is no specific location. Anywhere between 2 to 5, you can see a peak. It's just one peak. It's normally a broad peak. It doesn't split anything else. It's not splitted by anything else. So it's just always like a one short peak, and it is singlet, unless you have like 100% pure alcohol. In that case, it can be splitted or it can split, but finding because of the azeotrope, that's alcohol mixed with the impurity or with water, is going to never be like 100% pure alcohol. So you have you will always get it as like a single peak, anywhere between 2 to 5. So one more time, the type of information that you expect to get from NMR is number of peaks. Number of peaks, it shows how many different type of hydrogens you have. So if you have 1, 2, 3, 4 signals, and we don't count the 0 because that belongs to TMS, we know that we have 4 different type of hydrogen. And in this partial structure, this is like a CH3, CH3. So we have 1 type of hydrogen. So I'm just going to number it. So if this is like a 4 and this is 4, this hydrogen is 3. So we number 3. This hydrogen 2 is like 2 here. And then the hydrogen CH2, it's the 1. So we have 4 type of hydrogen. That's why we get 4 signal. The location of the peak, it shows how shielded or de-shielded the hydrogens are. If it shows higher than 2, that means there is an electron withdrawing group attached to the carbon carrying the hydrogens. If it's specifically single bonded to oxygen, that carbon is going to a peak between 3 and 4, and that's what we have here. Hydrogen from the OH and NH, there is no specific location, anywhere between 2 and 5, it will show up. And then we have this isopropyl that is like a multiplet or septet and is adjacent to a doublet that is coming from the CH3s from isopropyl. So we said if we have a septet and a doublet next to each other, this is coming from isopropyl group. Any questions that you might have? Okay, Questions? No questions? No. We already talked about the four different types of hydrogen in this in the previous slide. The coupling constant, okay, coupling constant or the J value. That is the distance between the if you have like a splitting like a doublet for a hydrogen, you have a doublet, there is a distance between these two, and that is known as like a J value, this distance. I don't want you to be worried about those values. You won't get many questions about it, but just have an understanding that if you have like hydrogens from the cis position is going to split, and you have the J value. If they are in the trans position, the J value is different. So is a method to distinguish between hydrogen in different position. So if there is like a free rotation, this J value normally is like 7. And if you have restricted rotation, this is like a cis. This is like a cis, and if it is cis, it's going to be 10. If it's a trans, it's going to be 15. If they are geminal, are in the same carbon, that is going to they split each other, is going to be like classified as geminal, and is going to be only 2. So based on the distance between in the splitting pattern, the distance between the 2 peaks, if this value it corresponds to either one of them, you can basically predict the type of hydrogens that you're dealing with. The hydrogen is being split by a trans, by a cis hydrogen, or is by a geminal carbon, geminal hydrogen. For the aromatics, this value is again, if they're in ortho position, or if they are coming from meta position, they are coming from para position, they are going to be different. So with ortho, meta, and para is going to be a different value. So for ortho, if it's 8, for meta is going to be 2. Just understanding the idea that the values for coupling constant is going to help you to determine position of the hydrogen on the same molecule. That's that idea you need to know, but exact numbers are not the concern, okay? Exact number, to memorize all these numbers is not the concern, but knowing that if you have like a hydrogen, 2 hydrogen in the cis position versus trans position, what type of information you need to distinguish between the two is the coupling constant. This idea you need to know. Memorizing the numbers, you don't have to memorize those numbers. Okay. Now, if you have a aromatic di-substituted aromatic ring, this is aromatic ring and is di-substituted, you have a methyl group and you have a nitro group. Okay. How many different type of hydrogen? Because it's solved problem, it's easier to review it, and that's where you should start. And then you go to problems that you don't have the solution, and especially like end of the chapter problems, because then you could reference the use the solution manual as a reference to make sure that you are answering those questions correctly. So first, you are going to determine how many different type of hydrogens you have. Let's say I'm going to use a different example, and then I go back to that solved problem. Let's say if you had a CH3 here and another CH3 and these hydrogens here, how many different type of hydrogens you have in this molecule, in the red molecule that I draw here. So if I call this CH3A, okay, and this hydrogen is going to be B, what should I call the hydrogen on the adjacent carbon, this hydrogen here with the arrow? Should it be A, B, or C? Which one? What should I name that? The hydrogen with the arrow? Should it be A, B, or C? B also, very good. So if this is a B, this hydrogen is going to also be B. This hydrogen on the left side, the one on the left side is going to be also B, and the bottom left also is going to be B, and the CH3 is going to be A. So we have only two types of hydrogen, A and hydrogen B. So we have hydrogen B and hydrogen A. Now, hydrogen A, what would be the splitting pattern for hydrogen A? Splitting pattern for hydrogen A. A singlet, doublet, triplet. For hydrogen A, what is the value for N? We are looking for N plus 1. What's the value for N? N means number of hydrogen on adjacent carbon, right? How many hydrogens do we have on this adjacent carbon? 0. Okay. 0 hydrogen. So the value for N is going to be 0 plus 1 is going to be 1, and that is a singlet. Do you follow me? So for hydrogen 1, we are going to get a singlet. Do you remember the location for hydrogen A? What is the approximate location for hydrogen A based on the table? Why is not 2 hydrogen? Because there is no hydrogen on this carbon. Is 0 hydrogen on the carbon, and 0 plus 1 is going to be 1. If you look at the benzene ring, this is a very common mistake. Benzene ring has 6 hydrogens. But if you want to replace one of these hydrogens with methyl group, then there is 0 hydrogen on this. So either is substitutions or hydrogen. If there is no substitutions, it's going to be a hydrogen. But if there is substitutions, you have alkyl group attached, there's no hydrogen there on that carbon. So if you take this hydrogen, you cannot add NO2 to that carbon. You must take the hydrogen away before you add the NO2, because this carbon already has 4 bonds, cannot have more than 4 bonds. So there is either branch or hydrogen on the benzene ring. So there is 0 hydrogen here, and 0 hydrogen plus 1 is going to give you a singlet. Now, so A would be singlet. And what's the location of A? What type of hydrogen is this? You have to memorize this. I know you don't have quiz for this chapter today. It's next Monday, but you need to start memorizing this number, have approximate value for these. This type of hydrogen, this is benzylic hydrogen. And if you look at the tables, is going to be between 2.5 to 3.5. So if I have like a 2 to 3 here, it's approximate, like proper approximation. Now, hydrogen B, at what number, what location hydrogen B is going to appear? Is aromatic hydrogen. Anyone with an answer? Aromatic hydrogen? They are very specific. We have aromatic, aldehyde, and carboxylic acid, very specific location for them. And I repeated at least like 3 or 4 times last class. Aromatics, they would appear between 7 and 8. So hydrogen B is going to appear between 7 and 8. And now, what would be the splitting pattern for hydrogen B? Hydrogen B, how many hydrogen you have on the adjacent carbon? So N plus 1, in this case, is going to be 1 plus 1, and that equals 2. So for hydrogen B, you're going to get a doublet. But since they're all the same, it's going to be 1 doublet. Okay, now going to the example that we have on this slide and this diagram, NMR spectrum. What we have here is that you have methyl group attached to carbon 1, and then you have a nitro group attached to carbon number 4. This is electron donor group, and this one electron withdrawing group. Okay, this is electron donor, electron withdrawing. So as a result, this hydrogen A is not going to be the same as hydrogen B, because hydrogen A is closer to electron donor group. Hydrogen B is closer to electron withdrawing group. So we have hydrogen A, hydrogen B. But this hydrogen is a carbon away from methyl group and 2 carbon away from NO2. Same thing as the hydrogen A on top. So we have 2 hydrogens that are identical. So hydrogen A, and this one is going to be hydrogen A. You have hydrogen B on a carbon adjacent to 1 carrying NO2, and then this hydrogen, similar situation or position, is going to be hydrogen B. So we have 3 types of hydrogen in this case, not 2. So we have 3 types of hydrogen. We have hydrogen A, B, and we have hydrogen C. Now, hydrogen C, this is called benzylic. Benzylic hydrogen is going to appear between 2 and 3. And that's what we have for benzylic. Hydrogen A and hydrogen B, these are called aromatic. And aromatic would appear at what location, what position? In what position you will see aromatic hydrogens? Between 7 and 8. Okay, please make sure to remember these numbers. These are very obvious numbers. It's going to help you, but the only way it can help you if you remember these positions, the numbers. So it's going to appear between 7 and 8. Now, if it's attached to electron withdrawing group, just like IR, if it's attached to electron withdrawing group, is going to shift to higher number. If it's attached to electron donor group, it's going to shift to lower number. Okay, it's going to shift to lower number. So based on the nature of CH3 and NO2, hydrogen A is closer to electron donor group. So hydrogen A is going to appear closer to 7. This is for hydrogen A. And hydrogen B would appear closer to 8. So our hydrogen B is going to appear at a higher number. So that's the location. It's going to be between 7 and 8, but still the one that is attached to electron withdrawing group would be closer to 8. The one attached to electron donor group would be closer to hydrogen. It would be closer to 7. Conjugation lowers the frequency. Electron withdrawing group would increase the frequency. Now, what about the splitting pattern? What do you think of the splitting pattern? What do you know about the splitting pattern? What would be the splitting pattern for hydrogen C? Would it be a singlet, doublet, or triplet? Hydrogen C. What is the value for N plus 1? I expect some responses because I want to move. to next slide, but I want to make sure that you follow me. What is the value for N for this hydrogen C, type C? We had very similar example like 2 minutes ago. It would be singlet, okay? It would be singlet because there is no hydrogen on this carbon. Number of hydrogen on adjacent carbon is 0. Aromatic ring is either has a branch or hydrogen. You cannot have a branch and hydrogen. So it's 0. Plus 1 is going to be 1, and that's why we have a singlet. And hydrogen A, what would be the splitting pattern for hydrogen A? Hydrogen A, what is the value for N plus 1, or what is the value for N? For hydrogen A, on this carbon on top here, on the right side where you have the CH3, there is no hydrogen. So on the left side, there is 1 hydrogen, and that makes it 1 plus 1, and that is 2. So you would get a doublet. So for hydrogen A, you get doublet. For hydrogen B, what's the splitting pattern for hydrogen B? What is the N plus 1 for hydrogen B? Is it going to be singlet or doublet? No response yet? What are you counting? You are counting number of hydrogen on adjacent carbon. How many hydrogen you have on this side? 0. How many hydrogen you have on the right side? 1. So it's going to be 1 plus 1, and that is 2. So you would get a doublet. So that's why you have a doublet, and a singlet for the CH3. So from now on, if between 7 and 8, if you see a doublet and a doublet, that means you have a aromatic ring that is di-substituted. And if it's di-substituted, with respect to each other, they are in position 1 and 4. So this is di-substituted. You have a methyl group and a nitro group, and they are in position 1 and 4, or para position. So if you have a di-substituted para di-substituted aromatic ring, between 7 and 8, you will get 2 doublet, a doublet and a doublet. Now, what happens if this is a meta? If it's a meta, let me see if the next example brings the meta. Otherwise, I will help you with the meta. No. Okay, what happens if you have a meta? The splitting pattern is going to be different. Say I put this in a meta position. Meta means that you have in carbon 1, CH3, and then carbon 3, you have NO2. So you have a hydrogen here, hydrogen, hydrogen, and hydrogen. This is meta di-substituted, okay? I hope you're taking notes, because if you don't take notes now, you have to take notes later, and then you don't have me to ask questions at that point. So I hope that you are taking notes now, so you know what you're writing. This is a meta di-substituted benzene ring. We determine the type of hydrogens, A, and then hydrogen, these 2 hydrogens, you have B, you have C, and then you have D. Okay? Or if you make it even, these, let's make it like same CH3. So it's away one away from the hydrogen. So it's going to make it simpler. And then I can go back to NO2. I do have the NO2 and the homework also. So we have A. So this is going to be B. And then you have B and C. So you get B, C, and D. Look at the splitting pattern. Yeah, you have hydrogen A. I need the location and a splitting pattern. At what location hydrogen A would appear, and what is the splitting pattern? We had two examples already. I'm sure you know it. Hydrogen A. If that's hydrogen A, this is also hydrogen A. What location? What's the splitting pattern? What type of hydrogen A is called? It's called a benzylic hydrogen, right? Benzylic hydrogen would appear between which numbers? Benzylic hydrogen would appear between 2 and 3. And benzylic hydrogen is going to be a singlet. So it's between 2 and 3. Now, between 7 and 8, you have hydrogen B, okay? Hydrogen B, you have hydrogen D, and you have hydrogen C. Hydrogen D is attached to 2 electron with donor group, so it's the closest to 7. So hydrogen D is going to be also a singlet because there is no hydrogen on these carbons. No hydrogens, no hydrogen. So hydrogen D is going to be singlet and closer to 7. So we have hydrogen B. This is the hydrogen A. I'm sorry, D. I said D and then, okay, this is a hydrogen D. Now, for hydrogen B is attached to carbon with 1 other hydrogen. So hydrogen B is going to be a doublet. We have hydrogen B, it's going to be doublet. And then hydrogen C, there are 2 hydrogens, one on the right side and one on the left side. So n plus 1 in this case is going to be 2 plus 1, and that is 3. So it's going to be a triplet. So if the di-substituted benzene ring, if it's para di-substituted, that means between carbon 1 and 4, you would get 2 doublet between 7 and 8. If it's meta, that means 1, 3, or meta di-substituted, meta is going to be singlet, doublet, and triplet. The splitting pattern between numbers of 7 and 8 is going to be different if it's meta or you have para. If it's ortho di-substituted, it's going to be, again, different from these two. So with the NMR, you can easily say if you have a ortho, meta, or para di-substituted. So if you have a ortho di-substituted, you only get like a doublet and triplet. So you are going to get like a doublet and a triplet. You're not going to get this singlet here. So you know that is a ortho di-substituted. The one that is, if we call this one hydrogen B and this one a hydrogen B is going to be doublet, and hydrogen C, we call this hydrogen C, and hydrogen C, this is going to be triplet. And it's obvious, it's kind of clear unless you didn't count the number of hydrogens properly. For hydrogen C, you have a hydrogen and the hydrogen B position, and then you have the other hydrogen C. So you count 2 for each one, and it's going to be 2 plus 1, that gives you triplet. Questions? Any questions you might have about the splitting pattern and what you're counting for a splitting pattern? Questions? So beside the pattern, like you have for ortho, meta and para. So if you have for ortho here, meta and then para. Beside the pattern that for para you have two doublet, for meta you have a singlet, doublet, and triplet, and for ortho you have a doublet and triplet. Also, the J value is going to be different, and from the J value you could also say if it's a ortho, meta, or para. Okay. The hydrogens are not labeled here. And can you tell me this singlet belongs to which hydrogens? The singlet that you have close to 1 or between 1 and 2 or 1 and 1.5 belongs to which hydrogens? If you can hear me. Yes, you can hear or you cannot hear me. Which hydrogens would appear as a singlet between 1 and 1.5? These are CH hydrogens. These are CH2 hydrogens. And these are the CH3 hydrogens. So is a CH, CH2, or CH3? In this location. You have 6 of them, is the most popular one, and is the tallest peak here between 1 and 1.5. So that belongs to the CH3. Then you have the CH2s. That is like a triplet, each one. The CH2s are coming from the hydrogen. If I label them, it's going to be hydrogen A and hydrogen B. Which one is hydrogen A and which one is hydrogen B? Between these two, which one is hydrogen A, which one is hydrogen B? I give you a hint, but I do expect an answer, and I hope that I get an answer. If it's closer to electron withdrawing group, it would appear at higher number. If it's closer to electron donor group, it would appear at lower number. So which one belongs to A, which one belongs to B? Hydrogen B, hydrogen A. So these are hydrogen A, and these two are hydrogen B. If I call this one 1 and 2 for simplicity, so hopefully I get an answer. Which one belongs to A, which one belongs to B? Is it 1A or 2B? A is closer to 3. Okay, very good. So this is hydrogen A, and this is going to be hydrogen B. And we know that these are triplets because it's adjacent to a CH2. If any hydrogen is adjacent to CH2, it's going to be a triplet. Then you have our CHs. So CHs, if we call them like a D and E, okay, D and E, then we have doublet for D and E, and they appear here. So if I call these again capital A and capital B, which one is capital A, D or E? Or you could say, is D closer to 6 or D is closer to 7? Hydrogen D. Okay. Hydrogen E is closer to 6 because it's adjacent to electron donor group. Hydrogen D is closer to 7 because it's adjacent to electron withdrawing group. So splitting pattern also is a doublet because on the adjacent carbon, you only have one hydrogen. Okay, the coupling constant that I said, or the J value, it can tell you if you're dealing with a hydrogen in the cis position, or if you have hydrogen in the trans position, or if you have hydrogen on the geminal position. Just know the idea, the concept. You don't have to memorize the exact numbers. Hydrogens that are equivalents or non-equivalents is like a stereochemical equivalence or stereochemicals non-equivalence is if you take one of these hydrogens and you replace it with the group Z, if the molecule becomes chiral, then we could say that the molecule or the hydrogens are non-equivalents. But if you replace it and still is not going to change the configuration or stereochemistry of the molecule, those hydrogens are chemically similar, or they are the same type of hydrogen. So if you replace hydrogen 1, hydrogen 2, or hydrogen 3, one at a time with the Z group, there is no change in the molecule, and still your molecule is a chiral molecule. As a result, hydrogen 1, hydrogen 2, and hydrogen 3 are identical. They are equivalent hydrogen. Hydrogen that they are chemically equivalent, they do not split each other. They split something else, another hydrogen, but they don't split each other. Like this hydrogen 1, 2, and 3 can split the hydrogen on CH2, but it cannot split each other. These hydrogens can be splitted by the CH2 as well. Okay, so they can split or be splitted by other hydrogen, but not to each other because they are chemically the same. But if you have a hydrogen, like a hydrogen A and B, in this case, that if you remove hydrogen A and replace with the Z group, you could get cis or trans. These hydrogens, these are like the vinylic protons. They are cis diastereomer. They would give cis diastereomer, or it would give a trans diastereomer. They are different, chemically different, and they can split each other. And if they do split each other, you'll see that J value. So the idea is hydrogens that they are similar or they have similar chemical environment, they are not going to split each other. But if they are different, they will split each other. So these 3 hydrogens in the CH3, they don't split each other, but these hydrogens from the CH3 can split the hydrogen from CH2, CHCl. And then the hydrogen from the CHCl can split these hydrogens from the CH3. Ultra pure samples of ethanol. I said, remember earlier I said that if you have an OH group, is not going to be split or splitted by another hydrogen on the adjacent carbon unless it's 100% pure, which in this case is like an ultra pure sample of the ethanol. So the OH group is going to show splitting. But as soon as you add some acidic or basic impurity to it, the splitting will stop from the OH and it will show as a single peak. So the OH group there's some impurity, even very small impurity, it would show as a single peak. But if it's ultra pure, it would show as a multiplet because it's going to be splitted by the adjacent hydrogen. The peak from OH and NH, there is no fixed position for them. So we cannot say for exactly would appear between 2 or would appear between 3 or 3 and at 3.5. It can go anywhere from 2 to 5 for the OH, and then sometimes for NH it says anywhere between like 3 to 7. So there is no fixed position. And they are always like a very short peak because the number of the OH per molecule is very small, is either like 1 or 2 maximum. It's very rare to have like 3 OH in one molecule. So the height is very short also. Sometimes this peak can be mistaken by the background noise. So we don't know if it's the noise or is it a peak. And they say to prove that you do have OH, if you deuteriate your molecule, if you deuteriate, basically you would mix your alcohol or amine with D2O. If you mix it with D2O and leave it for like 24 hours, the OH would change to OD. Because D doesn't have an odd mass, it will not show a peak in NMR. So this will disappear. So if you mix your sample that you didn't know that is actually OH, you mix it D2O and leave it for 24 hours and you take the NMR again, this peak would disappear. That is the proof that your molecule actually had OH or NH. Because for both OH and NH, if you add D2O, that's replacement for the H2O. This is the deuterium isotope of water, is a heavy water. If you mix it, leave it for overnight, all the OH would change to OD, and it doesn't show a peak in NMR. So you would see that is flattened. Some application for the for the NMR and for determining structure or formula, and like proof of presence or absence of OH. Basically, it's going to confirm that, yes, it was there because after you mix it with D2O, it disappeared. Carbon-13 NMR has a different scale compared to proton NMR. For proton NMR, you have 0 to 10, and then outer scale 10 to 12. This is for proton NMR. For carbon-13 NMR, you would have from 0 to like 220. The region is going to stay the same, but the numbers are different. For example, if the aromatic hydrogen appear between 7 and 8, between 7 and 8, you have the aromatic. The aromatic in carbon-13 NMR is going to appear beginning of the 3rd quart. So if you divide this by 4, so aromatic ring is going to appear here. The carbon from the aromatic ring would appear in this location, like 0, 50, 100, and then 150. So it will appear very similar to this, right? Beginning of the 3rd quart, it will appear. If you have alkane is going to appear between 0 and 50. So in carbon-13 NMR, it shows how many different types of carbon you have. So if you have this molecule, how many different types of carbon you have in this molecule? If I call this carbon A, what would I call this? A or B? A or B? If this is A, CO double bond, this carbon is going to be B, but the CH3 is going to be A. So I have 2 types of carbon, and the number of peaks is going to be 2. We get 2 signals for this. CO double bond is going to appear between, just like aldehyde, carboxylic acid, it was showing at the end of this for the aldehyde and then carboxylic acid. Very similarly, CO double bond is going to appear around 180, like higher numbers, between 180 to 200. So we know that the CO double bond is going to appear here, and the CH3 is going to appear in this location because it's attached to electron withdrawing group. If you didn't have the CO, it would be between 0 and 50. Questions? So basically, you have to count how many different types of carbon you have. And from the number of carbons that you have, you are going to see the different number of signals you have. Location for the CO double bond is going to be toward the end. So if you have aldehyde in proton NMR, usually is coupled with the carbon-13 NMR and proton NMR is drawn in the same graph or same spectrum. So you bring the carbon-13 as a supplement, like in a proton NMR, CO double bond is not going to show. Like for ketone, is not going to show. But for aldehyde, you have a peak between 9 and 10. But if you have a CO double bond, it would show a peak around 180 in the carbon-13 NMR. Conjugation with lower electron withdrawing group would increase the frequency. So the internal standard or the solvent that is used for carbon-13 NMR, it's like a chloroform, and similar to the TMS that is used for proton NMR. So here we are using solvent. As long as you know that these peaks belongs to the solvent, you don't have to worry about it. It's there. It's just because the solvent that is used is going to show the peak in that region. The splitting pattern for carbon-13 NMR, it usually counts the number of hydrogen on the same carbon, but it's normally not shown and not studied. All the peaks that you see is shown as a single bond. But if you see the splitting pattern, you don't count the number of hydrogen on adjacent carbon, you would count the number of hydrogen on the same carbon. So if this is coming from CH3, it would basically be a quartet because it's coming from a CH3. So it would be quartet. This is going to be a triplet because it's coming from CH2. And this is going to be singlet because it's coming from a carbon attached to other. There's no hydrogen on that carbon. But normally you see these peaks are all singlet. They don't show that. It's not very popular to show the peaks. So for TMS, we have CH3, and that's why we have quartet. And for the other molecules that you have, if you have a CH3 in the group, it's going to show as a quartet. This you have to have like a high resolution. So it would show actually the splitting pattern. If you have a peak with triplet, the signal, that means you have a CH2. And if you have like a carbon with no hydrogen attached to it, it would show a singlet. Okay, I am going to start